There we go. All right, so let's do these warm-ups. The limit as x goes to -2 from the left of f, right? So we find x equals -2. It's right here. We hop on the road to the left and start heading back towards it. And we're getting closer and closer to the y value, which is 2. Yeah. Okay. That also happens to be the function value. That's also f of -2. I'll go ahead and write that. That also equals f of -2. So you can see there that the limit from the left, in this case, equals the function value. I won't write it down, but what would the limit from the right of -2 be? -1. Right. Does +2 equal -1? No. When the limit from the left doesn't equal the limit from the right, what type of discontinuity do we have? That one's a jump. That's what we call a jump discontinuity. Is it removable or non-removable? Non-removable. Good, because you can't make it continuous there by redefining it. Those are fantastic shoes, by the way. Yours. I like those. I don't know if it's my glasses or they're really that awesome. That's awesome. Yeah, like a lime sherbet. Yeah, makes me hungry. Maybe so. Okay. What would be? Hey, look at this one. The limit as x goes to 3. What's up with that? Is that from the left or right? I didn't even write anything.
Because it has no exponent, Larry.
Is it from the left or right?
It's from
Both. Thank you, Aiden. How do you know it's both? It doesn't have a negative or positive. Yeah. So if it's going to exist, we have to look from the left and the right, don't we? Yeah, we have to look from the left and the right. And only if those two are the same will it exist. Okay. So let's go ahead and go to 3. The limit from the left is 0. The limit from the right is 0. Does 0 equal 0? Yep. So guess what the answer is? 0. Yeah. Now let's come over here and do this follow-up. What is the limit as x goes to -2 of f of x? We're backtracking now. The limit as x goes to -2. No, doesn't exist. Right. We just said the limit from the left was 2. The limit from the right was -1. 2 doesn't equal -1. Whenever the two one-sided limits exist but are different, the general limit is DNE, right? And that's what we write. We write DNE. So DNE means does not exist, right? And limits can actually fail to exist for any number of reasons. In this case, the general limit fails to exist because the two roads from each side are going to different y values. But look what we did last week. We also found that a limit at an x value could fail to exist for a different reason, right? Because the y values increase without bound. There is no limit to how high they will go, or they can decrease without bound. Okay, so DNE is kind of like a catch-all category. In fact, some people developed the mantra, when in doubt, DNE, because it encompasses a lot of different circumstances. And I'll say that's a great mantra if you add to the end, comma, and don't be in doubt, right? When in doubt, DNE, comma, but don't be in doubt. Know what you're doing, right? DNE does not exist. Vertical asymptote, non-removable infinite discontinuity. Okay, so y'all are nice and warm now?
Oh, yeah.
Yeah. Warm like the bats of the Red Sox last night. Holy moly, I know. I didn't mean to bring it up, Tyler, but dang, 3 grand slams in 2 games. 12-3. That was a rough one. All right. Let's go ahead and do example 5b. It says sketch the graph of that using your knowledge of transformations and then answer the following questions. So y'all had transformations in algebra 2, right? Yeah, you did. Absolutely. This has a parent function that after today, you need to know, okay? This is a transformation of the parent function y equals 1 over x, okay? It is called the reciprocal function. That's its name, the reciprocal function. Because all it does is it takes its input x and flips it, 1 over x. Now, looking at it, you know right away what value is not in the domain. What? No, in the parent function here. 0. X can't be 0. Is it a whole or a VA? It's a VA, right? Because you plug in, you get non-zero over zero. X doesn't divide out. Let's go ahead and sketch the graph. You might recognize it. Here's what the parent function looks like. Y-axis, x-axis. It does, in fact, have a vertical asymptote on the y-axis, okay? But it also has a horizontal asymptote on the x-axis. Yeah, I do. Yeah, I do. Thank you. Old habits, you know. It's faster for me to do it than to keep switching back and forth. But thank you. Yeah. And you can snap it too, just straight. I know. Yeah. So anyway, here's what a horizontal asymptote is basically. It's not a discontinuity. You could draw left and right and cross the horizontal asymptote. It doesn't interrupt the flow of the graph. So the vertical asymptote is the only asymptote that is a discontinuity. But there are other asymptotes, okay? Now, why is there a horizontal asymptote? That kind of implies that the y values approach it as we go out to the right. We call that the end behavior of the graph. Think of like a really large value of x, like way out here. When x is 10, what is the reciprocal of 10? 1/10, which is very what? Big or small? Small. Let's go out even farther to x equals 100. Plug it into the function. What's the reciprocal of 100? 1 over 100, which is even smaller. Come out here to the right off the screen like at 1,000,000. And when x is 1,000,000 way down the line, what's the reciprocal of 1,000,000? 1 over 1,000,000. What's happening to those ratios as x gets bigger and bigger? Smaller and smaller, approaching what number? 0. Yeah. 1 over 10, 1 over 100, 1 over 1,000,000, 1 over a zillion. It's approaching 0, right? Think about it as like 1 part P urine to whatever part water. Would you drink a cup of water if it was 1 to 10, 1 part P to 10 parts water? No. Okay. But what if it were like 1 to 100? Still no. Okay. What if it were 1 to 1,000, 1 part P to 1,000 parts water? Okay. What about 1 to 1,000,000? Still no. Still with the better. What about 1 to a gazillion? Okay. What about all the water in the ocean and just a little pipette dropper of P? Let's do it. What is the concentration of urine in the water approaching? It's getting more and more diluted, right? Right? It's approaching 0. Yeah, pretend it's like a fresh water, you know, and it's distilled fresh water. Restaurant ocean. Yeah, there you go. The concentration of urine for parts P per water is approaching 0. Will it ever be 0? Not if you pee in the ocean, right? So that means it's approaching 0. And guess what y equals 0 is? It's the x-axis. So I knew y'all would appreciate that analogy on a Monday morning. Here's what it looks like then. Here's what the graph looks like. In the first quadrant, it looks like this. Okay? It looks like that. And then a reciprocal of a negative number is also a negative number. So it looks like this. Yeah, it lives in quadrants 1 and 3. All right. That's a new parent function. It's a reciprocal function. It has a horizontal asymptote on the x-axis at y equals 0, has a vertical asymptote on the y-axis at x equals 0. It lives in quadrants 1 and 3. Okay. So asymptotes are kind of like gravity when it comes to graphs. They're irresistibly drawn towards them. All right. Memorize that graph. Okay. Right now, look at it, memorize it. You got it. It's easy to remember, right? It actually has what we call origin symmetry. We're going to study that later on. If you rotate it 180 degrees, like put your finger at the origin and spin it 180 degrees, it looks the same. Okay. Has origin symmetry. The domain is all real numbers except 0. What's the range? We haven't talked about that, but if we have a graph, we can look at the range. What y values does it take on? All of them? From negative infinity, does it get 0? No. The reciprocal of a number is never 0. 1 over a number is never 0. Because remember, a fraction is equal to 0 when the what is 0? The top, the numerator. And it's a 1. It's a constant. Is 1 ever 0? No. What about at Halloween when it goes dressed as 0? No, right? We already said that. Clothes don't make the man. It's still a 1 on the inside. So it never is 0. So the range is the same as the domain, everything except 0. All right. Now that we know what the parent function is, if we can think about what transformations are in this equation, And remember what those transformations do to any graph, we can sketch our new graph, okay? So what we're gonna do here is review what I call standard transformation form. Here's what standard transformation form looks like. You have y equals a times f of, and then inside you have b times x minus c. I guess I'll do this as a blue as well. And then you're back on the outside plus d. Okay, if you remember that from back in the day, A, B, C, D. What's nice about using A, B, C, D is you could do these transformations from left to right in alphabetical order. Because your Aunt Sally says you have to do multiplication before addition and subtraction. And if you notice, A and B are multiplied. When you multiply something, you increase it by a scale factor. So those are what we call your dilations. They're your stretches or your compressions, right? Think about like playing an accordion. Hey, it's almost Myron Florin time, although he's dead now. Who's the other guy? Alex Meixner. There you go. You're stretching and compressing. If it's on the inside with the X, that's horizontal stretch compressed. If it's outside affecting F, which is another name for Y, it's affecting the graph vertically. So those are your dilations. C and D are added and subtracted. So that's picking the graph up and just moving it left or right if it's C, or up or down if it's D. I remember doing that. And then, of course, if A is negative, it takes all your Y values and takes the opposite of them. So it's an X-axis reflection. And if B is negative, it takes your X's and switches them. So that's a Y-axis reflection. Let's see if we can put this into standard transformation form.
Yeah.
Algebraically, what I'm going to do is I'm going to pull that 4 that's in the numerator off to the side with that negative. Is that okay? Is that legal?
It is super legal.
Super legal. Good. Because it's really like -4/1. You could pull any factor from the numerator out front. And that's enough to get it into standard transformation form. That's it. So there's 3 transformations here. What would the negative do to this graph and any graph? Flip it across which axis? X-axis, right? That one's easy to remember because you have x squared that opens up. And then most of y'all know negative x squared opens down, right? So that flips it across the x-axis. So that's going to be an x-axis reflection. This is your A value. Absolute value of A is 4. So that's going to be a vertical stretch by a factor of 4. The Y values are 4 times taller. 1 becomes 4, 2 becomes 8, so on and so forth. And that gives you your final shape of the graph. And then the x plus 2, since it's with the x inside the function, picks the graph up and moves it 2 units in which direction?
Left.
Left. Excellent. Okay. If it's with the x, it has to be horizontal. And remember, anything on the inside with x is the opposite of what it appears to be in the equation. So +2 normally means to the left, but it's, I'm sorry, to the right, right? +2 is over there, but it's actually to the left. Okay. It's because you're grabbing values further down and plotting them over here. You pick this x value, bless you, at, let's say we pick x at 1. At x equals 1, we're going to take the x value that's really over here at 1 plus 2, which is 3. So we're taking that value from 3 and we're bringing it back to 1. See that? That's why it's opposite. You don't have to really understand that. That's cool if you do. It's an honors class. But just know, hey, reflect across the x-axis, vertically stretched by a factor of 4, move it left 2 units. Now, even though the last thing we did was shift it left 2 units, it's the first thing we do when we graph it. So let's go ahead and do that. -2, right there. That is where your new vertical asymptote is, okay? And that's why we do it first. You always graph your asymptotes first, always, because they become guidelines, literally, for what the graph looks like. Now, notice if I ask you just to find the domain of this function f, like if we hadn't been doing it by transformation, I would say, what's the domain of f? You would say, x can't equal -2. That's the only value that makes the denominator 0. And then you'd be like, hey, x plus 2 doesn't divide out, so it's non-removable, infinite, it's a VA. And sure enough, it is. Okay. But now we know we have this horizontal asymptote. When I pick the graph up and move it left 2, does that change the horizontal asymptote? If it runs east to west forever and ever and you move it 2 units to the left, doesn't it still run east to west? Yeah, we could do the horizontal asymptote shift dance at the next pep rally. What do you say? Would y'all come onto the floor and do this with me? Think about it. Think about it.
I'm in the band team.
Hey.
So I can't do it.
Gallagher can do the choreography for us, right? Although I think I already got it figured out, right? Yeah, thank you. Thank you. All right, let's go ahead and sketch it now. If we reflect it across the x-axis, this piece here is down here, this piece here is up here, right? So now it lives in quadrants 2 and 4, and then stretching it vertically by a factor of 4, that's going to be hard to show. We just know the graph's going to be steeper. So we really can't show the dilations. We just know that it's steeper. So let's go ahead and do that. We'll draw it in here. And oops, that's not where it went. That's where it used to be. We reflected it. It's in here now. Notice that the asymptotes kind of act like your new X and Y axis, if you will. There you go. Now, everyone look at my green graph and just say, hey, that looks exactly 4 times steeper than the purple graph. Ready? 1, 2, 3. Hey,
that looks exactly 4 times steeper than the purple graph.
purple. Very good. Purple. That's the same criteria that I'm going to use when I'm looking at your graph. I'm not going to measure it. As long as you can tell me that it's 4 times steeper, that's what's important. What's really important are the shifts in this case and the negative dilations, the reflections. Okay, now that we know what the graph looks like, go ahead quickly and answer these 5 questions. Okay, on your mark, get set, go. I'm going to take attendance. All right. So now that we have the graph, these should be real easy, right? What would be the limit as x goes to -2 from the left? What'd y'all get? Infinity is the preferred answer, right? Hop on the graph, start going towards it. As we get infinitely close to -2, your y values get taller and taller and taller, all right? What is also an acceptable answer, although not preferred, Allie? No, too late. DNE, pay attention. If those guys are distracting you, we have chairs in other parts of the room. And if you're distracting him, we have chairs out in the hallway. Very good. What would be the limit as x goes to -2 from the right? Negative infinity. Good. Also known as DNE would be acceptable. Not as nice to have, because remember, and we'll just remember this from the weekend, when you tell me that the limit at -2 from the right is negative infinity, you're telling me first and foremost the limit doesn't exist. Then you're telling me why, right? Because the y values decrease without bound. So it's a preferred answer. All right, what then would be the limit? And yeah, it has to be DNE. Here's why. You can't put 2 answers there. Okay, you can't put plus or minus infinity. Now, if they were both going up on the on either side, we could put positive infinity. If they were both going down on both sides, we can put negative infinity. But it's doing one of each, so we have to put DNE here. All right, now what is f of -2? Is it anything? Yeah, you look high, you look low, and you don't see anything. Now, notice we could do this. What if I define this new function h of x? Let's answer this. This is DNE. Let's just finish this first. Part E, is f continuous at x equals 2? Why or why not? It's continuous? No. Good. We'll say no first. Obviously no. And here would be the reason. Believe it or not, that the vertical asymptote is not the reason. The vertical asymptote is a consequence of how and why it's not continuous there. Okay. No, because you can mention any one of the 3 things. Okay. You can mention the road in. You can mention the bridge. Or you can mention the road out. That goes back to the 3-step definition of continuity. If any one of those 3 things doesn't exist, or any 2 of them exist and aren't equal to each other, you can't drive across. Does that make sense? So if any one of them fails to exist, or any 2 of them don't equal each other. So you could say because the limit as x goes to -2 from the left of f equals DNE. Okay, that would be there's no road coming in. Or you could say f of -2 equals dne. That's probably the easiest one because it requires the least amount of writing. Or I'll just put ors in between here. Or you could say the limit as x goes to -2 from the right of f doesn't exist. This has no chance of being continuous. Yeah. Oh, +2. Yeah, let's change that to -2. Thank you. That is a typo on my part. I need to fix that. Thank you. Yes, that's why you said yes. Let's look at +2. Now that we've done that, look at +2. Would the function be continuous at +2? Yeah, and it would be because the limit from the left equals the function value, which equals the limit from the right. And we could find that value if we plug it in there. It'd be -1, right? F of 2 is -4/4. Yeah, thank you, Aiden. Keeping me honest here. Well, you can always turn a mistake into a teachable moment here, okay? So if a function is continuous, all three exist, all three are the same. Otherwise, if any two don't exist, or any one of them doesn't exist, or any two don't equal each other, that's the reason you cite. Now, if you knew that these were DNE because they were vertical asymptotes, right? Positive infinity, negative infinity, and I didn't give you the graph, would you know that the function f had a vertical asymptote at -2? You should, because as x approaches -2 from the left, if we go up towards infinity, there's going to be a vertical asymptote there. That's why we call it a non-removable infinite discontinuity. So you need to be able to do it both ways, okay? Look at the notation, know what's going on there, or look at the graph and write the notation, okay? Perfect, perfect. And then, of course, it is continuous at 2. Now, what if I do this? Let's get into piecewise functions, which we kind of skipped at the end of 2.1. This is a introduction to piecewise functions. Do your math homework. We're starting a new section, a new 9 weeks. Piecewise just means, it's kind of like piecemeal, right? When something's piecemeal, it's put together with a bunch of different parts. Piecewise function. So we define it with an open brace like that. And all you do is you define it to be like a Frankenstein's monster, right? Since we're talking about kind of close to Halloween stuff, he just put random parts together and made this monster. Frankenstein was the scientist, not the monster itself. Or if you think of like the Greek centaur, right? It's part horse and part man, and it changes right there at the torso. So it's a hybrid, right? So as long as we still pass the vertical line test, as long as for each x there's only no more than one output, we can define the equation to be whatever we want. So what if I defined it to be my original function, -4/x plus 2, everywhere except at -2, okay? So that's what that means. It's kind of like a program. Piecewise functions are kind of like programs. If you know anything about programming, you know, you got if-then statements, right? Or that's what they used to be. What are they now, Chris? Are they if-then statements? They're still if-then statements. Okay, if, then, else, whatever. Depends on what programming. I learned BASIC and then I learned Fortran. Fortran is still what engineers use, right? But there's all kinds of stuff out there. If x is not equal to -2, then use this function. So everywhere except at the vertical asymptote, we're going to let it be the graph that we already graphed. Everyone okay with that? Okay, good. Now, else, or I don't know if they also use if then else statements. Otherwise, when x equals -2, otherwise, if x equals -2, let's define it to be, someone pick a number. It was, let's see, the score last night was 12-3. So the Astros lost by 9 runs, which seems like infinity. Let's just define it to be 9. Okay, there's no sharing violation here, right? We have all the values when x is not -2, which is to the left and right of the vertical asymptote. And now look, when x equals -2, we're defining it to be -9. So what would the piecewise graph look like? Well, it would look like everything that we've already sketched in green. And then right here, we would just have a dot, okay? And it would be right there at -9. Does that still pass the vertical line test? Yes. It absolutely does. Now, what are piecewise functions useful for? You think they exist in the real world? Yeah, not everything exhibits the same behavior at all times, okay, or in all places. Like if you think about something as simple as like the speed of sound in the atmosphere, that's a piecewise function, okay? At different elevations, the speed of sound changes. And it doesn't just get, the sound barrier doesn't get smaller as you rise. It actually increases, decreases, and then increases again, depending on what layer you're in. So you could define it as, you know, a piecewise function. That's what piecewise functions are useful for. All right, so now if I had this question, what would be the limit as x goes to -2 of h of x? If this is now my graph of h, would it change the limit from the left? No, it would still be infinity, right? Would it change the limit from the right? No, it would still be negative infinity. Would it change the general limit at -2? No. But would it change part D? Would it change f of or h of -2?
Yeah.
Yes, h of -2 now would be -9. 9 run loss. I put 9 there, but I meant -9. Sorry. They lost by 9. My bad. Bless you. Put a -9 in there. I plotted it as -9. I know. But they'll rebound. They will. Okay. Now I put a dot there. So does that change the answer to E? Is H now continuous at -2? I got a bridge now. I got a bridge. Can we cross? No way. The bridges don't connect to the road. The bridge, single bridge, does not connect to either one of the roads. This is why it's a non-removable discontinuity. There's no way to make those roads meet. Even if they were going up on both sides, there's no way to put a bridge down to make them stop going up and turn into each other. Okay, so this is a non-removable discontinuity. All right, note to self, recraft this question next year to include a piecewise option for H and roll with it at +2. Do one at -2, do one at +2. We call that the Aiden clause, right? Making a lemonade out of lemons, right? There you go. Oh, every year we can relate it to the 2021 Astros game 3 of the ALCS. Okay. Is it first one to 4 or first one to 3?
It's best of 7, so first to 4.
There you go. That's math right there. So Red Sox are up 2-1. All right. All right. So now that we've done that, we actually can define it. Here is kind of the official, it's in a box, it's official, the official 3-step definition of what it means for a function to be continuous at a particular x value. Call it x equals c, okay? F is said to be continuous then at x equals c. C is actually a finite x value, okay? If these 3 things happen. The limit from the left of f is equal to the function value, the bridge, which is equal to the limit from the right, okay? They all exist and they all equal each other. So if you want to come underneath here, you could say the road in equals the bridge, which equals the road going out. Okay, all exist. I'll say all 3 exist. Let's keep that number. All 3 exist. Okay, and all 3 are the same. We'll put the same y value. It's real intuitive, right? You're trying to cross safely. That's super important now. And notice again, 2 of the 3 requirements are y values that you didn't even really think about or have a notation for before this section, the limit, okay? The limit forms the foundation for calculus, the study of calculus, instantaneous rate of change, and accumulation at variable rates, okay? And you'll see why if you take calculus at any point. It's a fun class. All right, road in equals road out. Road in equals bridge equals road out. 3-step definition, okay? So now let's go ahead and do example 6. Kind of the same graph that we've been borrowing from, but we can use it again. Determine whether the function is continuous at x equals 0, just with or without justification, all right? Well, if you just look at it right here, here's x equals 0, right? Also known as the y-axis. Your math homework. Just looking at it visually, is this function in red continuous at x equals 0? Yeah. Intuitively, you could just see, it goes right through the point, right? You can imagine your finger going whoop, right through it. Okay. So that's cool to be able to look at it and say, yeah, we're not always going to have the graph. Okay. Now, even when you have the graph, it's another thing all entirely to write out the justification. Okay. Using the 3-step definition with the right notation. And that's what y'all are going to learn to do. Okay. So here's what we're going to do at x equals 0. Let's come out and get our analysis in place. Okay. Let's do the limit as x goes to 0 from the left of f. Let's look at f of 0, and let's look at the limit as x goes to 0 from the right of f. We've done this before. Focus first on getting the notation down. Road, bridge, road, from left to right. Remember, they both have inputs of 0, and they both have function values f, but take special note, again, in where they're located. Now we'll come back and evaluate it. Well, that's easy, right? If you have the graph, there's really nothing to evaluate. You can see that they all meet up at what y value? 1. So you go 1, 1, and 1. That's easy. Now here's your justification, all right? Since, or because, whichever you want to write, since 1 equals 1 equals 1, comma. That's super important. Could you put a statement in here instead of 1 equals 1 equals 1? Could you put since 7 equals 7 equals 7? That's another true statement, right? Would that work here?
Well, yes, it would be true. It wouldn't work for this.
It would be true, but it wouldn't work here, right? Because when I say 1 equals 1 equals 1 in this argument, we're referring immediately to all 3 of those ones up above. Okay, that's the fastest way to write all of this up here. You don't want to have to write this equals this all over again. That's a lot of writing. So when you write it out one time with the right notation and then you evaluate it, in that same problem, you can refer back to those numbers. Okay, since 1 equals 1 equals 1, comma, and then you answer the question in a complete sentence. F, or f of x, is continuous at x equals 0. So when we quiz over this, here's where the check distributions would come. Check, check, check for the notation. Check, check, check for the evaluation. Check here for the justification. Whoa, this is called the justification. You're using the evidence that you gathered up above, and you're telling me how you're using it. And then the answer, okay? And notice what I did on that final line. Notice I didn't say it is continuous, right? It's continuous. Don't use pronouns in here. Don't say it's continuous. Notice I didn't just say F is continuous either, did I? Because I have to specifically say where I'm looking. All right. So there's a lot of checks built into there. The notation now is each one check. All right. I want you to do the same thing now on this problem. I want you to do it at x equals 3. Okay. You do the analysis at x equals 3, just like we did. This might be the last thing we do today. Get your notation up and running first, then come back and evaluate all 3, justify, answer the question. Got 2 minutes left. Here's what you should have. I wrote the notation out first. Limit as x goes to 3 from the left. That's written under the limit. And then f of x on the same level as the limit. F of 3, limit from the right. Evaluate it. 0, -1, 0. Since 0 does not equal -1. F is not continuous. F is not continuous at x equals 3. Now, the last thing here, if I just told you this was a scenario, if I didn't give you the graph and I said, here, based upon this description, what type of discontinuity now, since we know it's not continuous, what type of discontinuity would we have based upon this evidence? A hole. Very good. Because remember, a hole is always going to exist when the roads line up, but the function value doesn't plug the hole, either because it's somewhere else like it is here, or it doesn't exist at all. So you should be able to recognize what's going on there from the description, and you should be able to write the description from the graph. We made a lot of progress today on a Monday morning, okay? Oh man, it feels like a Monday.
Yeah, I know.
Happy Tuesday, everybody. Happy birthday, John Lithgow and Mr.